2016 Canadian Open Mathematics Challenge, Part B. If the cubic equation x to the power of 3 minus 10x squared plus px minus 30 is 0, has three positive integer roots, determine the value of p. We have x to the power of 3 minus 10x squared plus px minus 30 is 0. Now this is of course of the form ax to the power of 3 plus bx squared plus cx plus d. And there is a formula known as Vieta's that helps us with regard to the roots. So there's three formulas actually. And the formulas are as follows. The sum of the roots, so let's just call the roots R1, R2, and R3. The sum is equivalent to minus b over a, where this is b and this is a, the coefficients. And then the product of the roots, that by Vieta's formula, I guess would be R1 times R2 times R3. That is equivalent to minus d over a, where this is d and that's a. And then there's another one which is a little bit lesser used, which is the sum of the products. And that basically means R1 times R2 plus R1 times R3 plus R2 times R3. That's equal to c over a, where this is c and that's a. Okay, so let's see what we get with these. So from the first one, we get that R1 plus R2 plus R3 is, well, let's use this equation, obviously, minus b over a. So that's going to be minus 10 over 1, right? Because my b is minus 10 and my a is 1, because this is like 1. Okay, so that basically is 10. So 10 is the sum. And then the product, R1 times R2 times R3, using Vieta's, is minus d over a, so that's going to be minus 30 over 1, which is 30. Okay, so the sum is 10 and the product is 30. So now we have to experiment. We normally, if you have three variables, you would need three equations. And we probably could get a third equation. The only problem is the third equation would introduce yet another variable. So let's just experiment with this. Well, what is 30? 30 is 2 times 3 times 5, right? So I'm just breaking that up to see what I can choose for my values. And the good news is that they're integers. So that makes it a little bit easier. Okay, let's see. Let's say I assign R1 to be 2, R2 to be 3, and R3 to be 5. If I multiply them, then they would, of course, equal 30. But what happens up here? Well, let's see. If R1 was 2, R2 is 3, and R3 is 5, well, guess what? They add up to 10. So that works. Perfect. So the assignment that I gave just from basic experimentation works. Okay, so what do they want? They want me to figure out p. All right, p. P is right up here. So that's where this third one comes in, the sum of the products. So that's R1 times R2 plus R1 times R3 plus R2 times R3, and that's c over a. So in our case, c and a are p and 1. Okay, so that works out very nicely. So that's just p. Okay, great. So that means p is equal to, what's R1? 2 times 3 plus 2 times 5 plus 3 times 5. So that's 6 plus 10 plus 15 is p, and therefore p is equal to 31. The squares of a 6 by 6 square grid are each labeled with a point value. As shown in the below diagram, the point value of the square in row I and column J is I times j. A path in the grid is a sequence of squares such that consecutive squares share an edge and no square occurs twice in the sequence. The score of a path is the sum of the point values of all squares in that path. Determine the highest possible score of a path that begins with the bottom left corner of the grid and ends with the top right corner. Okay. So, at first I thought, well, I guess if you want to maximize the score, use the maximum number. So that means if you were going to draw a path starting here and ending there, just use all the numbers. And then I tried to do that. But watch what happens when you try. You go here, then you go up here, then you go up there. You kind of follow the zigzag pattern. But at this point, you end up there, which is great. But you left out all these numbers. All those numbers would not be included in the path, and therefore would not be included in the sum, which is the score. So is there any way to include all of them? And I tried, I experimented. I went this way and this way. Again, I end up at 36. I leave all these out. So I thought, is there any way to include all of them? And you can't. You can't include all of them. But you can include almost all of them in a sort of a weird way. And I'll show you that weird way. Let's see if I can do it. So you start off here, and then you kind of go like this, right? A zigzag pattern. And then you go across like that. And if you do that, you include all of them except that 2. And of all the ways of doing it, this is the way that maximizes the score. It's just kind of experimentation. So then you just have to add up all of these. So it's really just 1 plus 2 plus 3 plus 4, all of those numbers, right? And I'll just let you add them all up. When you add up all the numbers in the grid, it's 441. Now, our sum does not include that 2 because that 2 we didn't reach. So I guess from the total sum, we subtract that 2. And when you do, you get 439. So it's one of those questions that you just have to fiddle around with to come up with the highest possible score of a path. A hexagon ABCDEF has AB equal to 18, BC 8, CD 10, DE 15, EF 20, and FA is 1. Angle FAB is 90 and angle CDE is 90. BC is parallel to EF. Determine the area of this hexagon. Okay, so first task I have is to draw it based on what they're telling me, and it's certainly not going to be drawn to scale, but I'll try to at least come within, close proximity to this, what it could look like. Oh boy. And then it comes down, I think, because you got to make a right angle. And something like that. And then I guess I'm joining these. Yeah, like that. And then let's label this now. This is A, B, C, D, E, and F. And let's label the distances based on what they told me. This is 118, I believe. Yeah. 8, 10, 15, and what's the last one? FE is 20. Okay. And then this is a right angle, FAB, and CDE is the right angle. Okay, so I think this is a pretty decent approximation of what this hexagon may look like. All right. Now what I'm going to do is I'm going to chop this in sections so that will allow me to figure out the area of this hexagon. All right, so let's explain this now. BC is parallel to EF. Okay, so that means this is parallel to that. I know it doesn't look like that. Sorry, but you guys can work with me on this one. This green line makes that into a triangle. This one, the red lines I've drawn so that they're perpendicular, like that. And that will allow me to break this up. So since this line and this line are parallel, or at least they should be, and these two are also parallel since they form a right angle, that's a rectangle. So I guess the area of the hexagon ABCDEF is really the triangle FAB, this one right here, plus this triangle right here, Or actually, another way of doing it, which I think is better, is just to look at it from that trapezoid, right? Is that the shape? You think I would remember my shapes? Yeah, it's a trapezoid. And so that will just put B, C, E, F, that trapezoid. And then I guess just the final triangle, which is down here, which is CDE. Okay, I think we should be able to do this here without too much problem. FAB, well, that's easy. 1/2 base times height, so 18 times 1. BCEF, I'll come back to a little bit later. CDE, that's easy. That's 1/2 base times height, so 10 times 15. So this looks like 9 plus BCEF. And then this one is what? 75? Yeah. So really it's just 84 plus BCEF. Okay, so now let's concentrate on that trapezoid BCEF. Okay, if you remember the area of a trapezoid, if this is A, this is B, and this is H, the area is A plus B over 2 times H. Okay, so that means BCEF is, my A is 8, my B is this guy, which is 20, which is floating there. So 8 plus 20 divided by 2 times H. Oh, so H is, I guess, this red. Okay, I got it. So I got to figure out H. Okay, shouldn't be a problem. Since if this was drawn to scale, you would notice that from here to here is 8, right? From there to there, since that's 8. And therefore, since that's 20, and this... I got it. I got to figure out these hypotenuses. Okay. So FB, that's easy. That's 1 squared plus 18 squared, which is what? 324 plus 1, so 325. Root is FB. And then this guy, CE, this hypotenuse. Let's see here. That will be... CE squared is 10 squared plus 15 squared, which is 100 plus 225, again, 325. Root would be CE. Okay, so that makes this an isosceles trapezoid, since that is equal to that. Okay, that makes it easier. So I'm one step closer to figuring out the H. If this is 325 root, from here to here, since it's isosceles, I can figure it out now. This whole thing is 20, right? So you subtract from it the 8, that leaves 12, and then each of those is half. That's 6, and that's 6. I got it. Okay, so that's 6. Now I can figure out this H, which is what I have to put in here. Okay, let's just do it on the side here. 6 squared plus H squared is 325 root all squared. So that means H squared is 325 minus 36, and therefore H squared is 289, and therefore H is 17. Okay, great. So let's see, crunch out these numbers. We get 14 times 17. So 84 plus 14 times 17 is what? 238, and therefore the total is 322. Yeah. Okay, so had to do a little bit of Pythagoras and that kind of stuff, but wasn't too bad. Let n be a positive integer given a real number x. Let bracket x be the greatest integer less than or equal to x. For example, 2.4 is 2, 3 is 3, pi is 3, and so on. Define a sequence a1, a2, a3, so on, where a1 is n and am equals the bracket of am minus 1 over 3 for all integers m greater than or equal to 2. The sequence stops when it reaches 0. The number n is said to be lucky if 0 is the only number in the sequence that is divisible by 3. For example, 7 is lucky since A1 is 7, A2 is 2, A3 is 0, and none of 7, 2 are divisible by 3. But 10 is not lucky since A1 is 10, A2 is 3, A3 is 1, and A4 is 0, and A2, which equals 3, is divisible by 3. Determine the number of lucky positive integers less than or equal to 1,000. All right, so let's first explain this question by just using their example. They start off with A1 as 7, right? So to get A2, you have to use this formula. So you got to take the previous one, which is 7, divide by 3, and take the greatest integer less than or equal to that. So this is what, 2.3 approximately, and the greatest integer less than or equal to that is 2. So that's how they got A2 equal to 2. Then to get A3, you do the same thing. You take the previous one, which is 2, divide by 3, and this is what, 0.6, and that is 0. The greatest integer less than or equal to 0.6. So that's how they got A3 0. We can do it again. Now, before I do it again, let's explain why this is lucky or not lucky. It's lucky if 0 is the only number in the sequence that is divisible by 3. So what is the sequence? 7, 2, and 0. Of those numbers, the only one that's divisible by 3 is 0. 7 is not divisible by 3. 2 is not divisible by 3. So therefore, the number 7 is lucky. Okay. All right. So let's do one more, which is, let's just use their example, which is the next one, A1 being 10. A1 this time is 10. So A2, you take 10 divided by 3, and then you take the bracket. So that's what? 10 divided by 3 is like 3.3. So 3.3 is 3. And then again, you do this. So A3 would be 3 over 3, and that's just 1. And then A4 would be 1 over 3, and that is 0.3, and that is 0. So now let's talk about this. Now my sequence is 10, 3, 1, and 0. Of these, which are divisible by 3? Well, this one's divisible by 3, and so is this one. So since we have something else that's divisible by 3, this is not lucky. So not lucky. 10 is not lucky. So that's basically the question. Now we are told, determine the number of lucky positive integers that are less than or equal to 1,000. So between, I guess, 1 and 1,000, which is obviously 1,000 integers, how many of them are lucky? Well, obviously you're not going to go through them one by one, trying it for 1 and then 2 and 3, and then you get up to 7. You say, oh, look, 7 is lucky. There's a good one. That would take forever. So there's got to be some system. And there is a system. That system is converting to base 3. Now, if you're not familiar with how to convert a number to base 3, I will explain it. It's not that difficult. What you do is you first write out the powers of 3, and I'll just write out a few of them. So 3 to the power of 0, 1, 2, 3, 4, 5, and so on, right? Okay. And then what is the value of each of these? Well, this is 1, this is 3, this is 9, this is 27, this is 81, this is 243, and this is 729. And then I'll give you an example. Let's say I say to you, the number 235, write that in base 3. How would you do that? Okay, well, I have to use only these numbers. Well, I mean, this keeps on going, but I don't need to use any of these numbers that are bigger because 235 will be able to be accomplished with just, I guess, just these ones. And they have to add up to 235. And you're only allowed to use the numbers 0, 1, and 2 because it's base 3. You can't use the other digits. So, for example, I estimate that this is going to be a 5-digit base 3 number. So I'm going to have to use the 81 twice. So that's why I put 2. I think I'm going to have to use the 27 twice, the 9 twice, and I won't need this 3 and I won't need this 1. So I put 0 since I'm not including it. Now I say, well, why is this 235? Well, watch. This is 2 times 81. This is 2 times 27. This is 2 times 9, and this is just 0. 0 times 3, 0 times 1. Now let's do this. This is 162, this is 54, this is 18, this is 0 and 0. And these should add up to 235. And, I forgot it doesn't. It adds up to 234. Okay, no problem. So that means I need another 1. So this one has to be included. And I put a 1 this time, like that. So that means that this will be 1 and this will be 1. Okay, good thing I caught that. So this will be 1 times 1, which is 1. So now this should add up to 325. Let's see. 180, 234, 235. Okay. So that means that 2,2,2,0,1 to the base 3 is 235. And I encourage you to experiment with other numbers. Just make up a number in base 10, whatever, right? 750, whatever number you want, and then see what the base 3 representation is. Okay, so now that you're an expert there, let's talk about the question. The question is asking what's lucky and what's not lucky. In particular, between 1 and 1,000, how many of them are lucky? Well, here is the conclusion that you have to come to. A number is divisible by 3 if the rightmost digit is 0. So, for example, 22200, the rightmost digit there is 0, and therefore this is divisible by 3. Well, if you recall, 22200 was 234. Is 234 divisible by 3? Yeah, it is. 234 divisible by 3 gives you an integer. So that's what they mean. That's what they mean by this statement here. So now let's go back and talk about the whole lucky stuff, right? We are told how many of those n's are lucky. N is lucky if once you divide it by 3, then the next number also cannot be divisible by 3, right? Because you notice how it started off here, and then when we did the division by 3, the next number is not divisible by 3. So we want none of them to be divisible by 3. So n is lucky if none of the digits in base 3 of n is 0. Because watch what happens. If you start off with a number that, say, has like this, right? And then you divide by 3, immediately this is a number that is divisible by 3. So this number, 234, is not lucky because we found immediately a number that's divisible by 3. But let's say it was not immediately divisible by 3. Let's say you had 22201, right? Which, as I showed up here, is 235. Okay, let's go with that. 235, then we go through this whole thing. Let's say this was my A1. Then A2 is 235 divided by 3, that bracket business, right? So that's what going to be about 78 point something, and that's when you drop the bracket, it's going to be 78, right? Well, guess what? 78 is divisible by 3. 78 divided by 3 is what, 26? Yeah. So that's basically showing you that now this number 235 is not lucky because we just found a number that's divisible by 3. And you say, well, why was it not lucky? Well, I just showed you why, but in particular in base 3 because there's a 0 in there. As soon as you get a 0, that's when the problems begin. So this statement is very important to conclude to that n is lucky if none of the digits in base 3 of n are 0. So we have to essentially find numbers in base 3 that have no zeros. They only have the 1 and the 2. So, for example, 22211, that number is, what is that number actually? 238? Okay, so that's A1. Now watch what happens. If we do A2, it's really 238 divided by 3, correct? So 238 divided by 3 is about 79.3, and therefore when you drop the bracket, it's 79. A3, well, you take 79 divided by 3. And let's see what happens. 79 divided by 3 is 26.3. And when you drop the bracket, you get 26. Now, so far, none of these are divisible by 3, right? 238 is not divisible by 3. 79 is not divisible by 3. 26 is not divisible by 3. And let's just keep going. A4 would be 26 over 3 bracket. 26 divided by 3 is 8.6, which is 8. 8 is not divisible by 3, and so on. So if that hopefully proves to you that if none of the digits are 0, you will be able to get a lucky number. And I encourage you to sort of take this to the finish line, which we can just do it here. A5 is 8 divided by 3, which is what? 2 something, 2.6. So that's 2. And then I think one more, which would be A6 is 2 divided by 3, which is 0.6. And yeah, we got it down to 0. So our sequence was 238, 79, 26, 8, 2, and 0. And none of those are divisible by 3 except 0. And therefore, we conclude that 238 is lucky. All right, so I hope that example makes sense. So let's go back to this point that n is lucky if none of the digits in base 3 of n are 0. Okay, so that means we want numbers that have no zeros. So we'll make a little table, number of digits in the number, and then the examples, and then the total. Okay, so we have 1 digit, 2 digit, 3 digit, 4 digit, 5 digit, and 6 digit. What are we going? We're going up to 1,000, right? So what's 1,000? 1,000 in base 3, I think is, we can do this pretty quickly. 729, 243, 81, 27, 9, 3, and 1, right? So 1,000 in base 3, I think would be 1, which is 729, plus 243. Yeah. This will be 0 plus 27. This will be 0, 0, 1. I believe that's 1,000 in base 3. Yeah, because it's 729 plus 243 plus 27 plus 1. Yeah. So that means the largest number will have 1, 2, 3, 4, 5, 6, 7. So we want obviously numbers that are less than or equal to that 1,000 in base 3. So we only need numbers that have 6 digits because this 1,000 has 7 digits and that's the maximum, and this has zeros in it, so we know that for a fact it's not going to be lucky. So if a number has 1 digit, the only possibilities we have are just 1 and 2. So there's 2 of those in base 3. If a base 3 number has 2 digits, it could be 1, 1, it could be 2, 2, it could be 1, 2, or 2, 1, and there's 4 possibilities there. If a base 3 representation has 3 digits, it could be 1, 1, 1, 1, 1, 2, 1, 2, 1, 2, 1, 1, 2, 2, 1, 2, 1, 2, 1, 2, 2, or 2, 2, 2, and there's 8 of those. And then, you can kind of keep it going from there. What you'll see, what I noticed is this is 2 to the power 1, this is 2 to the power 2, this is 2 to the power 3. So by the same extrapolation, there will be 2 to the power 4 for 4 digits. For 5 digits, there will be 2 to the power 5 possibilities, and for 6 digits, there will be 2 to the power of 6. So this is what? 16, 32, and 64. So the grand total is the sum of this, which is 126. So all of these guys are base 3 representations, and they only contain a 1 and a 2. There is no zeros. No zeros. And when there's no zeros, based on my big long explanation up here, if there's no zeros, n is lucky if none of the digits in base 3 of n is a 0. And the total number of such n between 1 and 1,000 is 126.